Hi students, in today's lesson we are going to continue our discussion on periodic table. So today we'll talk about group 7 elements. Okay, so let's jump straight into it. So the elements in group 7 of the periodic table, again they have a special name. Okay, they are called the halogens. So as we have seen in the chapter on atomic structure, group 7 elements, they are non-metals, right? So as you can see in this small cutout over here on my cursor, group 7 of the periodic table is on the right hand side of the staircase of the imaginary diagonal line. So therefore, they are non-metals, okay? And we also know from our earlier chapters that Group 7 elements, they exist as diatomic covalent molecules, right? So for instance, if we look at this over here, we have fluorine, chlorine, bromine, iodine. All these, they exist as diatomic, okay? Meaning the chemical formula for fluorine is F2, followed by Cl2, Br2, and I2. Now, as I've shared before previously, the way to remember, right? So diatomic molecules, you can take it as you see the word D, right? You can think of the word double. So double means two, right? So diatomic means diatomic molecules just means that the molecules are made up of two atoms. Okay, so that's why F2, Cl2, Br2, I2, and so on. Okay, so quick recap in terms of terminology. So we have seen this term, right, monoatomic. That one is for group 0 elements, which we will cover in the next part. And then diatomic, which is 2, like I just said. And then we have also heard of this term called polyatomic, right? So molecules which are made up of 3 or more atoms, it will then be called polyatomic. Poly means many. All right. Okay, so now that we have talked about naming of the group 7 elements, now let's move on to look at physical properties of halogens. Okay, so the first one will be that in terms of melting and boiling points, they have very low melting and boiling points. All right, so this is, if you compare it to what we just saw last lesson on group 1 elements, you'll notice that this point is similar, right? Low melting and boiling points. But the reason why Group 7 elements have low melting and boiling points. This is very much different from that of Group 1. And in fact, for this, you have seen it in covalent bonding. Okay, so I'm just going to give you like 3 seconds to think about it. Why is it that the halogens have low melting and boiling points? Okay, let's count to 3. 1, 2, 3. Okay, if you cannot remember, right, I suggest you pause this video, you have a think about this, and then you start the video again, and then I will explain to you. Okay? Okay, so the reason why halogens have low melting and boiling points, and as I've said, you have learned this before in covalent bonding. So let's have a look at this, right? This was our notes from chemical bonding. Under structure and physical properties of covalent compounds. So like we mentioned earlier on, group 7 elements are covalent molecules, right? So over here, I'm going to bring up a molecule. Can you see? Yeah. Okay, so this, I will call it fluorine, okay? Because fluorine is the first, if you look over here by my cursor, fluorine is the first element in group 7. Okay, so it is 2.7, right? With 9 electrons in total, 2.7. So it has only 2 electron shells, so it's quite small. The atom is quite small. Okay, so this is fluorine gas, F2. So F2 is a covalent molecule, right? So most, like what we have seen previously, let's just quickly do a recap. So most covalent substances exist as simple molecules, okay? And in this molecule, for instance, the one that I'm holding, fluorine, right, F2, the atoms, which is in this case one fluorine atom and another fluorine atom, okay, these atoms in this fluorine F2 molecule, they are held by strong covalent bonds. So which means to say this grey color, stick over here, if you will, this represents the strong covalent bonds. Okay, so again, this is very important. So I'm just gonna recap. Why do we say that covalent bonds are very strong? Because if you look at this model that I'm holding, if I uh, were to want to break this bond, right, I will have to do this. Yeah, right, break and then break. Okay, so it's gonna take a lot of effort. So that would symbolize or represent that covalent bonds are very strong. It requires a lot of energy to break it. Okay, whereas if you look at the next sentence, we talk about this, right? The molecules, however, they are held together by weak intermolecular forces of attraction. So it's just like over here, we use the example of water, right? Let me look for my water molecule. So water. Okay, so again, say water is also a covalent molecule, correct? So within each water molecule, the oxygen and hydrogen atoms are held together by the strong covalent bond, right? If you look at the image there, right? But between the molecules, there's this invisible, you can't see, okay, but there's this weak intermolecular forces of attraction. So these forces of attraction, it's intermolecular, right? Means between molecules. So this is uh, very weak, right? That's why it's called weak intermolecular forces of attraction. It's very weak. So therefore, if you see the notes, very little energy is required to overcome these forces of attraction, which are holding the molecules together. So that was the reasoning as to why our covalent simple molecules have very low melting and boiling points. Okay, so yeah, so likewise for our case of fluorine, it's like that. Okay, then if I were to, let's say, bring up another molecule, this is let's say we call it, let's say, chlorine, right? Do you notice that it's a bit bigger? Fluorine is smaller, chlorine is bigger, all right? Which is expected because again, this topic is periodic table, right? We talk about periodic trends. If you look at the periodic table with me, chlorine, maybe I should put it this way, chlorine is below fluorine. Okay, so um, chlorine is in period 3, fluorine is in period 2. So obviously chlorine has one more electron shell, right? Chlorine has 3. Chlorine is, the electronic configuration of chlorine is 2.8.7 versus fluorine, which is 2.7. So obviously, obviously, chlorine has to be bigger than fluorine. Okay, you look at the ball, right? The ball is made bigger. Okay, yeah. So hopefully that helps you understand and appreciate how really when I say the concepts, you cannot learn the concepts on its own because everything will start to come together. This is what I mean. Okay, so yeah, back to our slides on group 7. Okay, so yeah, group 7 elements, first physical property is that they have low melting and boiling points. Second point will be that they are colored. Okay, so let me show you some images of how each of the group 7 elements look like in terms of their appearance. Okay, so I've written here for you, but let me give you some visuals to have a closer look. Okay, so in this table, you can see some data that we have for the halogens, right? So fluorine, chlorine, bromine, iodine, as well as the last one, astatine. Okay, so the table shows you the melting point, boiling points, as well as the appearance. So let's talk about the appearance a bit more. Okay, so we say that the halogens, one of the physical properties of the group 7 elements is that they are colored. Okay, so group 7 elements actually, if you do chemical reactions in the lab, if you involve them, actually it's very exciting because they're colored. Okay, so not so boring colorless or just a very dull color. They have very interesting colors. So for instance, fluorine, it is a pale yellow gas. Okay, for fluorine, right, fluorine is super reactive. Okay, yeah, so to be honest, fluorine in its elemental state, meaning F2 gas, right? It's actually very rare. Okay, it's very hard to get access to it because it's so reactive. Of course, it's also very expensive. Okay, but in the higher level labs, if you do actually look at it, it's a pale yellow gas. Okay, but for chlorine, the next one is quite common. It is a greenish yellow gas. So if you look at my cursor, I'm pointing, right? Okay, so chlorine looks like this. It looks pretty nice. Then for bromine, okay, bromine, as we go down the group, okay, again, as we talk about periodic table elements, we always think about trends. Okay, so as we go down the group, bromine, in terms of color, it becomes slightly more intense. Okay, it is a reddish brown color, and in terms of the state that it exists as at room temperature and pressure, it becomes a liquid. Okay, so reddish brown liquid for bromine. Bromine is more common lah. You should have seen bromine before, possibly. Okay. Then for iodine, right, for even further down the group, and if you look at number of electron shells that iodine has, it has quite a number, right? Depending on which period it is. Iodine is 2, 3, 4, 5. Period 5. Okay, so it's really quite a huge molecule already. So if you look at trends, right, then obviously iodine will definitely be more intense in terms of its color, and true enough, it is purplish black, okay, and now iodine in its elemental state, it is a solid. Okay, so for this thing about iodine, right, very commonly we hear about iodine solution, okay, but please take note that iodine solution is different from elemental iodine, because iodine solution basically just means you take iodine and you dissolve into uh, a solvent, right? So that's why you form iodine solution. Okay, so that's why you might be thinking, hey, shouldn't iodine be brown? Okay, not really. Iodine solution is brown, but iodine I2 iodine molecule itself is a purplish black solid. Okay, then if we go down to the last one, which is astatine, the color intensity increases even more. Then it's actually a black solid. Okay, so this is for you to appreciate. So if we do a quick summary of the periodic trends of the physical properties of group 7 elements, it will be as follows. As we go down group 7, the melting and boiling points of the halogens will increase, right, as what we have seen over here, the trends, and the colors of the halogens will become darker. Let's now have a look at the chemical properties of halogens. So first and foremost, we need to understand that halogens, they are reactive non-metals. Okay, so quite similar to group 1 in the sense that they love to react, right? And so far from atomic structure, like I said, we already understand why this is so, because they want to achieve the stable octet or duplet electronic configuration, right? So group 1 metals, they will readily lose that one electron, whereas the halogens, they will readily gain that one electron, okay, to form the stable electronic configuration. That's why they are very reactive. Okay, halogens, they will react with most metals to form salts. Okay, and these salts, we have a special name for them. They are called the halides. Okay, so basically this will help you understand in terms of why the naming is as such. So meaning to say, let's say if the halogen that is reacting with the metal is is fluorine, then it will form a fluoride. If it's chlorine, then it will form a chloride, bromide, iodide, and so on. Okay, so meaning to say, if we go back to examples that we already know, which is, and we are very familiar with, which is sodium chloride. If you think about it, basically it's just when the halogen, in this case chlorine, reacting with a metal, sodium metal, to form sodium chloride salt called sodium chloride, which is a halide. Okay, so that's what the naming means. So halides, right? Yeah. So examples of halide ions will be fluoride. Basically, these four lah. Okay. So fluoride is F minus, chloride is Cl minus, bromide Br minus, iodide I minus. Okay. So all have 1 minus charge because they're in group 7. So for group 7, you need to know two chemical properties. Firstly, the halogens, they will undergo displacement reactions with halide solutions. Okay, so first and foremost, right before this, we went through the terminologies. So what are halogens and then what are halides, right? So be very sure about these terminologies, because otherwise your understanding for displacement reactions will just be all the place, all like everywhere. So a displacement reaction is a reaction in which one element takes the place of another element in a compound. Okay, so that's like a definition. So how does it work? So there's this box over here, right? It says don't forget, because this particular reaction is very important. Okay, so what happens during a displacement reaction? What is the main concept that goes behind will be that a more reactive halogen will displace a less reactive halogen from its halide solution. Okay, so if we look at the positioning of the group 7 elements in the periodic table, right, again, the ones that are on top, so such as fluorine, which is right on top, fluorine is the most reactive halogen. Okay, so basically what this is trying to say is that a more reactive halogen, let's say for instance fluorine, okay, so fluorine gas F2 is able to displace a less reactive halogen, let's say chlorine, from its halide solution. So this is very much like English. So a less reactive halogen from its halide solution. So meaning in this example that I just mentioned to you, the halide solution will be a chloride solution. Okay, so meaning again, a more reactive halogen, in this case fluorine, it is able to displace chlorine out of the halide solution, chloride solution. If we look at the example, over here it says when chlorine water is added to aqueous sodium bromide or potassium bromide, a reddish brown solution is obtained. So over here we know from the periodic table that chlorine is more reactive than bromine, right? So again, chlorine is above bromine, so the tendency of it gaining that one electron to form the stable octet is a lot higher. Okay, so in this case, chlorine is able to then displace bromine from the bromide solution. So if we were to represent this piece of information into a word equation, this is how it will look like. Okay, so chlorine, which is light yellow in color, it will react with sodium bromide solution, so basically a salt solution, which is colorless, and then immediately you'll see the color change. Okay, so it will form sodium chloride as well as elemental bromine, which is reddish brown. Okay, um, so this is a displacement reaction, right? So you can think of it as the chlorine is kicking this bromine out of its bromide solution, okay, such that now it takes its position, okay, to form sodium chloride, and then bromine is being produced in this case. All right. So you can also take this one step further to represent it in a chemical equation. So we will have more practices on writing chemical equations as well as getting your chemical formulas right. But for the moment, you can still figure it out from the information that's given to you in this part. So they tell you chlorine water, right? So this means that chlorine has already been dissolved in water, which is the solvent. So in this case, you're going to write Cl2, and your state symbol has to be aqueous. So AQ. Then sodium bromide is NaBr. In this case, it's a salt solution. So again, solutions always is AQ, right? The state symbols. Yeah. Then sodium chloride, same thing, also AQ, NaCl. And then bromine, in this case, because it is dissolved in water, again in the solution form, so it's Br2 aqueous. So, and then finally, for chemical equations, check that. So number one, check that you have your chemical formula correct. Number two, check that you balance the chemical equation. And then finally, make sure you have the correct state symbols. Okay, so we will have more practices on that. Now let's watch a video to see how the displacement reaction happens in the chemistry lab, and hopefully with the visual representation and by seeing how the color changes work, you'll be able to appreciate this reaction a bit more. So let's have a look. So over here you'll see that there are three different test tubes, okay, filled with different halide solutions. Okay, you're going to add aqueous chlorine into each of them. So first one is a chloride solution, second one is bromide, and then third one is iodide. Okay, so you're going to add aqueous chlorine into each test tube. So notice that the first one, there's no change. Second one, there's a color change. And then third one, there is also a color change. Okay, so let me pause this right here. So if you look at it, right, let me try to scroll it a bit. Okay, so right, so initially, again, let's think back. So the video is very fast, but let's talk through it. So over here, we are adding aqueous chlorine into each of these three test tubes, right? So chlorine in this case is the halogen, right? Chlorine is the halogen, and then these are the halide solutions. So chlorine is over here, right? If you look at the periodic table, it's right there. Okay, so for the first test tube, you are adding chlorine into a chloride solution. Okay, so it's like their own kind, right? So in that sense, in that case rather, there is no reaction happening. Okay, and which is true because you see that there is no color change, correct? It just remains colorless, so there's no reaction. Second test tube, okay, where's my finger? Second test tube, all right, you are adding chlorine, which is more reactive, into a bromide solution. Okay, so if we go back, if you just scroll back to the notes, right, to your own notes, you flip back to your own notes, have a look at what displacement reaction is again, right? Your chlorine being more reactive, it will displace bromine from the bromide solution, which is why you saw that, right? After that, you see that there's a color change, and notice that over here, uh, yeah, there's a chemical reaction. The displacement reaction has already happened. Likewise, for the iodide solution over here, all the more, right? Because chlorine is much more reactive than your iodine. So again, your chlorine will displace iodine from this iodide solution. And this is what you saw, right? It turns a bit reddish brown, right? Because iodine in solution, which is what you're familiar with, right? Iodine solution is brown in color. Yeah, so something like that. Okay. Okay, so to wrap things up, we have this table over here showing you the displacement reactions of some halogens with potassium halides. So, yeah, so if we just have a look at the example that we saw right in the video just now of the experiment, okay, we had chlorine adding into a chloride solution, a bromide solution, and an iodide solution. Okay, so again, if you add chlorine into a chloride solution, nothing is going to happen. All right, there's no displacement, right? You can't displace yourself out of a halide solution of yourself in that sense. Okay, so this case it is blacked out. There's nothing going on, no reaction. Okay, or rather, there's nothing to talk about, like, right? Why would you even do such a reaction in the first place? Okay, so there's nothing here. Then chlorine with a bromide solution, then the observation will be that your chlorine will displace bromine from the bromide solution. Okay, so this is the chemical reaction with the accompanying observation in terms of color. Then for iodide, right, chlorine adding into iodide solution, similarly, your chlorine, right, because obviously it is the more reactive out of the two, so it will again displace your iodine from the iodide solution. Okay, so if we now move downwards, move down the periodic table, right? So below chlorine is bromine. So if you look at bromine, if now you're adding bromine, right, the halogen bromine into a chloride solution, okay, there is not gonna be any reaction, right? Because bromine being a less reactive halogen than chlorine, it has no abilities to so-called kick chlorine out of the chloride solution, right? So since it doesn't have the ability to do that, so then nothing will happen. So there's no reaction. There's no displacement reaction. Okay, so that's why here it says no reaction. Then we move on, right? So then again, same thing, bromine cannot kick its own self out of the solution. Nothing will happen over here, so there's nothing to talk about. And then if we talk about an iodide solution, then your bromine can displace iodine from an iodide solution. Because if you again look back at the periodic table, bromine is still above iodine. So bromine is still a more reactive halogen than iodine. So bromine is able to displace iodine from its iodide solution. Okay, and then if we follow that train of thought, then obviously if we go to the halogen iodine, it is unable to displace chlorine out of its chloride solution. Neither is it able to displace bromine out of the bromide solution. And of course, itself, we don't need to talk about that. Okay, so this is basically the summary of um, displacement reactions. The first chemical property of halogens that you need to know. Okay. Okay, so if we talk about periodic trends, so after learning about displacement reactions, we look at trends, right? So we can now deduce the order of reactivity of the halogens from their displacement reactions. So if we compare to what we just learned before this, which is on group 1 metals, right? Alkali metals. So for group 1, just as a quick recap, the reactivity of the alkali metals increases down the group. Okay, but for halogens, it is the opposite. Okay, the reactivity of halogens actually decreases down the group. Okay, so what is the reason? The reason is because the size of the atom increases down the group. This one we can understand fully, right? Because as you go down the group, there are more and more electron shells, so your atom increases in size. Okay, so for group 7, the difference is that um, over here, group 7 elements, they are trying to gain one more electron, correct? So if your size of the atom increases, right, then it becomes more difficult, okay, making it more difficult for the nucleus to attract one more electron, okay, because again, the nucleus is positively charged because of your protons, and then your electrons are all negatively charged, right? So whether or not it is able to attract that one more electron to fill the outermost shell or the valence shell really depends on how far your electron shell lies, the last one. Okay, so if you look at chlorine over here, it is already quite big. So can you imagine for bromine and iodine, it's just going to get bigger and bigger. Your nucleus is going to get further and further away from your valence shell. So therefore, the reactivity of the halogen decreases down the group. Okay, so you can conclude that the order of reactivity is as follows. So chlorine is more reactive than bromine, which is then more reactive than iodine, and so on and so forth. Moving on, we will talk about the second chemical property of halogens, which you need to know. So halogens, they are powerful oxidizing agents. So in group 1, we said that alkali metals are powerful reducing agents. So now this is on the flip side, right? So halogens, they are powerful oxidizing agents. During chemical reactions, the atoms of halogens, they readily gain electrons, right, in order to achieve the stable octet electronic configuration to form halide ions with a charge of -1, which was mentioned at the start of this chapter, right? So at this point in time, where you are still in secondary 3, this is pretty much all that you need to appreciate and understand, okay? But when we go on to Sec 4 and we learn oxidation and reduction, which is redox in short, then you will be able to fully understand and appreciate this reaction, okay? But for now, if you look at this example, basically this is what we have seen so far, right? The halogen, which is things like your fluorine, chlorine, F2 and Cl2, right? So as represented by the symbol X, okay, X2. So it's going to gain electrons to form the halide ion, which is of a charge of 1 minus, right? So yeah, you might be wondering how come here got 2 coefficient 2, right? This is because we need to balance the chemical equation, okay? Yeah. So Yeah, so displacement reaction between halogens as well as other halide ions, it is a redox reaction. Okay, so why is it called a redox reaction? Because uh, in a displacement reaction, both oxidation as well as reduction takes place in one particular reaction. Okay, so in this case of, let's say, the displacement reaction between chlorine as well as potassium bromide, okay, your bromide ions, they are oxidized to bromine. The chlorine is reduced to the chloride ions. So in this case, chlorine will act as the oxidizing agent because it is reduced, whilst your bromide ion will act as the reducing agent because it is being oxidized. Okay, so you might think that I'm speaking alien language because you haven't learned redox, but like I said, come Sec 4, you'll understand this part. Okay, so for now, really, this is the portion that you need to understand, which is very closely linked to atomic structure as well as chemical bonding. Okay, just to show you the overall ionic equation for this reaction, which eventually you also learn, right? Now you learn chemical equations. Next time, very soon, we will start to look at ionic equations. Okay, so looking at how uh, the different species will react in the form of the representation in the form of ions. Okay, so yeah. So when we learn redox, then all these will make sense to you. So over here, chlorine, Cl2 is being reduced to the chloride ion, and then your bromide ion is being oxidized into Br2 bromine. Okay, so yes. So redox, the way to remember will be in terms of electron transfer. Oxida- uh, Oxidation is the loss of electrons, whereas reduction is the gain of electrons. Yeah. Okay, so as mentioned, for this part on the second chemical property of halogens, at Sec 3 level, you don't have to be overly worried about this part. More importantly, you need to be able to appreciate the understanding behind the displacement reaction, which is the first part, and be able to write the chemical equation as well as the possible observations that you will see in a particular experiment, for example. Okay, and that will be good enough. And then, of course, when we go to um, Sec 4, then this part on redox will become uh, quite a huge understanding that you need to have actually for this reaction. Okay, but yep, that's it for now. This is the end of the lesson for Group 7 elements, which we can also call them halogens. Goodbye.